Hello all, welcome to Physiology by Dr. Shanmugh. So today we are going to discuss about the basics of membrane potential, its formation, that is its generation to establishment of resting membrane potential. So okay, imagine you have a cell in the early developmental stage. Okay, these are early developmental stage cells. Now it has a nucleus. It has a nucleus, and this contains all the information for protein synthesis which happens with due course of time. Initially, in a cell, there will be a lot of channels which are permeable and leaky. There are a lot of channels which are permeable and leaky. So the permeability is not highly selective, but it's free. Among these, most of these channels are leaky and permeable for potassium more than sodium. Now, as you see, the charges of proteins inside the cell, they are negative, right? But these proteins cannot cross the membrane. They cannot cross the membrane. So they are fixed inside the cell. Non-permeable charges. And these proteins will attract the positive molecules. Agreed. So what are the positive ones? Moreover, the abundant channels are that of potassium. So there will be potassium influx or movement inside the cell to balance this. Okay. Even some sodium also will come inside. Some sodium also will come inside. Very, very less comparatively. Okay. It will look like almost this potassium and one sodium. The ratio is very high when it is potassium to sodium. So intracellularly potassium is high, very, very high. So this is the first gradient, potassium chemical gradient that is formed. Eventually what happens, the sodium also comes inside, but the sodium is not a ion which is desired inside the cell. We will know the reason in a while. So what happens here, the first movement of potassium here to balance all these charges, this is almost the Nernst potential of potassium is established. Here the Nernst potential of potassium is established. That means the Nernst potential is the voltage at which the net movement of a particular ion is 0. That means its electrical gradient and chemical gradient are almost equal. Electrical equals chemical gradient. It's almost equal. And now, because of this Nernst potential is established. But these are not the only ions which are present in the body. Eventually, there is a development of other channels with increased transcription and expression. Now we have potassium channels, we have sodium channels, we have chloride channels. Okay, and this will lead to redistribution of all these ions, because the charges inside the cell, that is the fixed charges, that is the protein, is impermeable. It means the membrane is impermeable to the protein. These cannot move. So it will lead to redistribution of potassium, sodium and chloride. Okay, please understand. Hope you understand why all this, just to balance just to balance the charges and maintain electroneutrality, that is equilibrium. But this condition is not favorable for survival, because if sodium goes inside so much, what happens? It will carry water along with it. It will carry water along with it inside the cell. But if the water is increasing, this will lead to cell swelling. Okay, this is prevented by one major development, sodium potassium ATPase pump. So what does this pump do? This pump, it will pump 3 sodium outside and 2 potassium inside. 3 sodium outside and 2 potassium inside. So initially what is there? There is high chemical gradient of potassium inside, right? Because of the Nernst potential, there is high chemical gradient. So this will move out because of the chemical gradient till the chemical gradient becomes equal to electrical. This will create negative charge. Because movement of positive ion from inside to outside the cell. So if you remove positive from the inside will become negative, 1 negative. If you remove like that multiple positives, it will become multiple negatives. So inside of the cell becomes more negative. They will settle at around minus 90 initially, if there is only movement of potassium. But there is also redistribution and the action of sodium potassium ATPase pump. This will lead to again pumping back of this potassium inside. So all of this taken into account, it will settle at minus 70 millivolts. That is the resting membrane potential. So what is the basic reason that RMP exists? It is the potassium efflux through leaky channels. This is the first reason that the RMP exists, because initially when there is nothing, potassium was there inside, and because of the chemical gradient established, it will start to move out. So that is the first thing. Because of this only the RMP exists, right? Again, if this is the case, how is it maintained? It is maintained by again filling up the potassium which is outside the cell by pushing it inside the cell. This is by sodium potassium ATPase pump. So it is providing the inside of the cell with more potassium to push it out. Simple. So this will cause maintenance of the RMP. Then what is the primary function of sodium potassium ATPase? As we discussed here, sodium carries water. Here the sodium carries water. It has to be stopped because it causes cell swelling. If you want to remove sodium, you have to activate the sodium potassium ATPase pump. What is the primary function of sodium potassium ATPase pump from this point of view? It is prevent cell swelling. Got it? By removing sodium by removing sodium from inside the cell. So this is how there is establishment of RMP and maintenance of RMP, and there is maintaining the cell volume. Okay, it prevents cell swelling and maintain cell volume. So why is this required? It is required for the vital functions of the cell. Vital functions of the cell. Everything is perfect here till now. Now where does this Nernst potential and Gibbs-Donen come from, and what is Goldman Hodgkin Katz equation? So this is the question. So here we have to see that Nernst equation is represented in the equilibrium potential of ion X is equal to the RT by ZF. Okay, and concentration of that ion outside the membrane by inside the membrane. Okay, and this is, we can see that R is the gas constant, universal gas constant, and T is the temperature, and F is the Faraday constant, and Z is the valence of the ion. For example, if you calculate this, you get Nernst potential of potassium is around minus 94. Okay, we discussed minus 90, which is also fine. Sodium is plus 60 millivolts, and calcium is plus 130, whereas chloride is minus 80 millivolts. Okay, now I want to give you a statement. The RMP of a membrane is close to the Nernst potential of potassium. Okay, please observe this. We have seen the normal RMP is around minus 70 millivolts approximately, right? RMP is minus 70 millivolts, and which is closer to minus 80 rather than minus 94. Here comes the important role. Okay, among chloride and potassium, potassium is the most abundant and most diffusible ion. Okay, among all of this, most diffusible ion is potassium, which is the first ion to start the establishment of membrane potential by moving out of the cell. So it is closer to that of potassium. Please remember. Okay, if anybody asks you, this is the reason. Moving ahead, if you see that multiple ions are involved in the membrane potential, final membrane potential, that is potassium, sodium, chloride principally. Okay, because all other ions will move in and out very minor manner or only in specific conditions. Okay, perfect, right? So if we take all of these into account, we will have a better equation where membrane potential is equal to minus 60 millivolts log 10. Concentration of the potassium ion inside by outside plus all of this sodium chloride. You can see all of this. This is the sum of all the concentrations. See here, the chloride is outside by inside because it has negative charge on it, and these two have positive charge. Got it? Now, if there is any other negative ion for X, it will become outside by inside. Very simple. Now this equation is called Goldman Hodgkin Cad's equation. Very, very important and very, very simple. Okay, this comes around, the total comes around minus 70 or to minus 74 millivolts, something around, based on the concentrations. But roughly we can take minus 70 millivolts. Okay, this is the resting membrane potential because of all these diffusible ions. Got it? This is very, very important, and this is the most simplified form where you will understand the Nernst, and it is simple. Outside by inside Nernst potential, you can add multiple ions potential, but in a sequence manner, numerator by denominator. Okay, not fraction, multiplication of fraction, but numerator by denominator sum. And whereas the Gibbs-Donan equilibrium is where there is redistribution of diffusible ions due to fixed intracellular non-diffusible charged particles or ions like proteins. So it is influencing, very, very simply, it is influencing the diffusible ions. It's like a senior citizen in the house. If you consider the cell as a house, okay, if you consider the cell as a house, this is how we used to draw, and inside this there is a senior citizen inside the wheelchair. Okay, when you want to see this grandmother, you have to go inside, but she won't come out, right? So it is only influencing, and if the house is having a capacity of 10 people, 10 people will go in. Only after these come out, others will go in. It is the redistribution. To neutralize her desire to see everyone. Very simple, right? So this is how Gibbs-Donan. It's a very, very lazy equilibrium, I call it. Just because the proteins are there, they're very lazy, they cannot diffuse, they will redistribute the other diffusible ions. It's act like a boss. So if you have any doubts, please mention in the comments. Like, share and subscribe to this channel. Thank you.